Let's see if we can learn a thing or two about carboxylic acids. Carboxylic acids. They have the general form. They still have that carbonyl group, just like we've seen in aldehydes and ketones. And they will be part of a longer carbon chain. But instead of having a hydrogen here, as the case with an aldehyde, or having another carbon chain here, with the case of a ketone, we have an OH group. Just like that. And you're probably saying, hey, why is this called an acid? It must be called an acid because it is an acid. And you'd be right. And the reason why it is an acid and why it is more acidic than just something with an OH group, so the reason why it is more acidic, it's actually a good bit more acidic than alcohols, is because once this thing loses its hydrogen, remember, acids, depending on what type of acid you want to think about, acid in the Lewis sense could be an electron taker, and this oxygen can take the electron of this hydrogen. Or if you think about the Arrhenius definition of an acid, it is a proton donor, and this OH group can donate a proton. It takes away the electron of this hydrogen, gives away the proton. Either way, but the reason why this is more acidic than an alcohol is once it gives away this proton, it is actually resonance stabilized. So let me show you what that means. And to do that, let me actually show you the bond between this oxygen and this hydrogen. So the oxygen and the hydrogen, see the oxygen has that, or the oxygen has this pink electron, and the hydrogen has that purple or that magenta electron right there. If you put this in a solution of water, so you have some H2O over here. You have some H2O. You have some H2O. This oxygen right here really wants to take back this magenta electron. So it really wants to take back that magenta electron. And as it takes back that magenta electron, it would essentially donate the hydrogen proton to a water molecule. So the water molecule would give one of its electrons to the hydrogen proton and then become positive. So once this happens, the next step would look like this. What was our carboxylic acid will now turn into the carboxylate ion. So it will now look like this. So it has our carbonyl group. Now this oxygen just took an extra electron. It just took an extra electron. So it has, so if I want to draw it, I have that one. Actually, let me draw. So this is the oxygen. To start off with, the oxygen had 2 lone pairs. So I want to draw those 2 lone pairs first. So to start off with, it had those 2 lone pairs. And now it had this pink electron from the get-go. And now it took this magenta electron. So now it has 1 extra valence electron. It has, we can even draw them here. We can count them. 1, 2, 3, 4, 5, 6. 6 is just a neutral oxygen. But now it gained another one. It has 7. It now has a negative charge. And then the water has now become has become a hydronium ion. So you have the water here. We've increased the proton or the hydronium concentration in the water. This one water molecule is now a hydronium molecule. So this is now bonded with this hydrogen proton just like this. This oxygen gave away an electron to this proton, so now it has a positive charge. And this right here, this carboxylate anion, carboxylate ion, right over here. The reason why this thing was a stronger acid than something that just had an OH group is because the conjugate base, the carboxylate ion, is actually resonance stabilized. It is more stable than the conjugate base of an alcohol. And let me show you that. This thing can share its negative charge. It can give an electron. It can, let me draw it. It can take this magenta electron, give it to this carbon. Then this carbon will have an extra electron. So then it can give back an electron to this top oxygen. So then it can give back an electron to this top oxygen right there. So it is resonance stabilized with this structure right over here. Let me draw the same. So it could look like this. That's too big. Let me scroll down a little bit. It could look like this. Carbon. And now this took back this blue electron. So now that one of the bonds is gone, and it now has, it started off with two lone pairs. So I want to draw that there. And now it has another lone pair. It has this electron, and now it has that blue electron right over there. And now this oxygen, this top oxygen, has a negative charge. And now the carbon has a double bond with this side oxygen. So now the carbon, let me go back to the yellow. That's the first bond with that oxygen. It had 1, 2 lone pairs to begin with. And now it has this magenta bond. So this pink electron is at this end. And now this purple electron is at the other end, or this magenta electron. And now it has a double bond with this oxygen. And we know that when you have resonance stabilization, it's not like you're going back and forth. The reality is that you kind of have a half double bond between both oxygens, that the electrons are just flowing across the whole place, and that stabilizes the molecule. And so to show that this is a resonance structure, let me put some brackets around it. Let me put some brackets around it. And in general, if this R group right here is actually even better at withdrawing electrons, so if you put something that was really electronegative here, something that likes to hog electrons, it would make the carboxylate ion even more stable. It would make the carboxylic acid even a better acid. So if you put something electronegative here, then you could imagine that some of this negative charge that we drew in these two resonance structures can be sucked to that R group, and then that would make it even more stable and would make the carboxylic acid even more acidic. Now, like in everything we've looked at, there are some common carboxylic acids that are not systematically named that it's probably a good idea to know. And I'll start with one, and just to see the pattern that we've seen in other things. I mean, we've seen that this thing over here, if we have this, we call this acetaldehyde. This was the very simple aldehyde we studied. We saw that if we have something like this, which is a ketone, we call this acetone. So you can imagine what we're probably going to name. Let me do this in a different color. What we're probably going to name this molecule. This molecule right over here. This is a carboxylic acid, clearly. And it has just that one methyl group, just like the acetaldehyde, just like the acetone. And so this is acetic acid. Acetic acid. So the acetaldehyde, acetone, and acetic acid, for me, are fairly easy to memorize just because they all have the acete part. They all have that as their prefix. And this part of the molecule is identical in every case. And the difference is the hydrogen, the methyl group over here, or the OH group, making this one a carboxylic acid, and acetone, and all of that. Now, a couple of other ones that it wouldn't hurt for you to know. Is this one right over here. This is, you could argue, even simpler than acetic acid. And this is formic acid. Formic acid. And then another one, and actually I recently did a general chemistry video with this, where we did a titration example. But this is essentially two carboxyl groups attached to each other. It looks like this. Two carboxyl groups attached to each other. And you could see them. This is one carboxyl group right over here. And then you have another carboxyl group right over here. And so this actually can be deprotonated twice. This hydrogen can be lost, and that hydrogen can be lost. And this is oxalic acid. Oxalic acid. I'll leave you there, and in the next video, we'll learn how to systematically name carboxylic acids.